Hey, thank you for watching this presentation about the poster we've presented at the GN&C conferences here in Breckenridge. Let's say we are in a parking orbit around an asteroid and we would like to descend to the asteroid surface to either land the spacecraft or to deliver a payload that may land on the asteroid. Um, we have some initial state at t0, and we would like to perform a maneuver at time t1 such that we arrive at our targeted location R2 at time t2. And after we arrive at that target location, we will perform another maneuver to match the surface velocity of the asteroid. So we have given the time t1 at which we want to perform the first maneuver, and the target time t2 where we will also execute the second maneuver, and we have given our target location R2. We would like to find the two delta V maneuvers, delta V1 and delta V2, such that we match the surface velocity of the asteroid at that targeted location. To do that, we use a guidance algorithm based on solving Lambert's problem. So Lambert's problem basically finds a orbit that connects two locations, R1 and R2, for example, with a given time of flight in between those 2 points. So this time of flight in our example would be t2 minus t1. The algorithm that we developed uses the Lambert solvers based on Gooding or ITSO, so you can specify which one you would like to use in our software. And the algorithm also automatically checks for constraint violations. So let's say we would like to get to R2, but our solution for that maneuver would cause us to be on a trajectory that intersects the asteroid, then that will be a constraint violation. So we want to have some minimum orbit altitude, for example. This could be a bounding sphere around the asteroid. And for the second maneuver, we assume that the state of the spacecraft is equal to the velocity solution of Lambert's problem. The reason for that is that there might not be enough time for the navigation filter to converge to a solution. So if those two maneuvers are very close together, we might not have a very accurate estimation of the state at T2. And so for that reason, we assume that the state at T2 is equal to the position corresponding to R2 and the velocity corresponding to the solution of Lambert's problem. The way we've set up this algorithm is that first, there's a Lambert planar module within the Basilisk astrodynamic simulation framework. Lambert planar basically sets up the geometry of the problem and prepares the Lambert's problem to be solved by the next module, which is the Lambert solver. Lambert solver then solves the Lambert problem given our parameters such as the targeted location and the initial location and the time of flight, and then computes the velocity required at the first maneuver such that we are on that transfer trajectory. Finally, there's the Lambert validator, which will check the constraint violations, and only if there are no constraints violated, and also if the solution is actually converged and we're not changing the solution a lot from one time step to another, then it will compute the required delta V, delta V1 to get us to that targeted location. Once we're at that targeted location, there is the Lambert surface relative velocity module, which computes our required inertial velocity such that we match a desired surface relative velocity of with respect to the asteroid. And with that, we have the last module, which is Lambert second TV, and this module will compute the second delta V that's required to match the surface velocity. The numerical simulation is done using the Basilisk Astrodynamic Simulation Framework, which is developed for a large part in the ABS lab. And we dispersed the initial conditions with both position and velocity dispersions, and the results show that we arrive at the targeted location with errors with mean errors of a few centimeters and with a standard deviation of about a meter or less. And the surface velocity errors are relatively low, in the order of millimeters per second for both the mean and standard deviation. So in conclusion, we found that the proposed onboard guidance law may be used for asteroid proximity operations, and to reduce final errors, we could actually chain these maneuvers one after the other. So we have multiple of these first DV1s, and that way we kind of can go from one gate to another to reduce the time of flight between the first maneuver and the second maneuver.